Hello again. This is Math 1220 coming to you from the College DuPage, and the title of this lecture is Linear Programming Word Problems. As always, be an active learner when watching these videos. In this chapter, we show several word problem applications of linear programming with two variables. Example 1 is called office purchases. An office manager needs to purchase new filing cabinets. He knows that ACE cabinets cost $40 each, require 6 square feet of floor space, and hold 8 cubic feet of files. On the other hand, each XLO cabinet costs $80, requires 8 square feet of floor space, and holds 12 cubic feet of files. His budget permits him to spend no more than $560 on new filing cabinets, while the office has room for no more than 72 square feet of cabinets. The manager desires the greatest storage capacity within the limitations posed by his funds and space. How many of each type cabinet should he buy? So the solution begins by defining variables. So we let X represent the number of ACE cabinets to be bought, and let Y represent the number of XO cabinets. The information given in the problem can then be summarized in the following table. This is dealing with the ACE cabinets. This is the XO cabinets. So we call this one X, we call this one Y, the number of cabinets. The cost of each cabinet, the space required for each cabinet, and the storage capacity for each cabinet, and the maximum available dollars and square feet to use. The constraints imposed by cost and space then are, the cost is $40 for every one of the ACE cabinets plus $80 for every one of the XO cabinets has to be less than or equal to $560, and the floor space is that 6 times the number of ACE cabinets plus 8 times the number of XO cabinets must be less than or equal to 72. The number of cabinets cannot be negative, so X is bigger than or equal to 0 and Y is bigger than or equal to 0. At this point in time, we're not insisting that these be integers, but of course they must be. So the objective function to be maximized gives the amount of storage capacity provided by some combination of ACE and XO cabinets. From the information in the chart then, the objective function is Z is equal to storage capacity is going to be 8X plus 12Y. So in summary, the given problem has produced the following linear programming problem. Maximize Z equal 8X plus 12Y, subject to 40X plus 80Y is less than or equal to 560, 6X plus 8Y is less than or equal to 72, X is bigger than or equal to 0, and Y is bigger than or equal to 0. So what we do is, and it does take time to do this, but a graph of the feasible region is shown here below. So we here graph 6x plus 8y equals 72. Here we graph 40x plus 80y equal 560. Here is x bigger than or equal to 0. Here is y bigger than or equal to 0. And we put all those together and we get this as the feasible region. We solve for the corner points. So the corner points are 0, 7, 12, 0, and 8, 3. The corner point theorem says that the maximum value of z will happen at a corner point, so I plug in those corner points into the objective function, and I see that the maximum space happens by buying 8 of the ACE cabinets and 3 of the XO cabinets, and we end up with 100 units of storage. And we state our solution this way. The maximum happens when x is equal to 8, y is equal to 3, and so the manager should buy those arrangements of cabinets. The next example involves nutrition and involves a minimization problem. Certain laboratory animals must have at least 30 grams of protein, at least 20 grams of fat per feeding period. These nutrients come from food A, which costs 18 cents per unit, and supplies 2 grams of protein and 4 grams of fat. And food B, with 6 grams of protein and 2 grams of fat, costs 12 cents per unit. Food B is brought under a long-term contract requiring that at least 2 units of B be used per serving. How much of each food must be bought to produce the minimum cost per serving? Again, we define our variables. We let X be the amount of food A needed and Y be the amount of food B. And we summarize the information that we read in the table here. This row deals with food A. This deals with food B. And the minimum requirements are grains of protein is 30, and grams of fat, this is grams of protein and grams of fat, are represented here. So we use the table to develop the linear programming problem that we have to solve. Since the animals must have at least 30 grams of protein and 20 grams of fat, we use greater than or equal to constraints here for protein and fat. So those are the constraints. The long-term contract provides a constraint not shown in the table, but y has to be bigger than or equal to 2. Clearly, x and y must be bigger than or equal to 0. And our objective is to minimize the cost. Z equals 18 cents per unit of food A and 12 cents per unit of food B. This is a minimization problem. So again, we graph the constraints. Now, the constraint y is bigger than or equal to 0 is superseded by y bigger than or equal to 2. But here is y equal to 2, and y bigger than or equal to 2 goes this way. This is constraint 2x plus 6y equal 30. Here, we're bigger than that. And this is the constraint 4x plus 2y equals 20. And when we shade those regions, we get this unbounded region. And when we solve the equations simultaneously, including x equals 0 and y equals 0, or greater than 0, y greater than or equal to 2, I guess, we get these as corner points: 0, 10, 3, 4, 9, 2. And so those are the corner points that we evaluate the objective function for, and we find that the minimum happens at 3, 4. So the minimum value of 102 occurs at the point 3, 4. Thus, 3 units of food A and 4 units of food B will produce a minimum cost of 1.02 per serving. One measure of the risk involved in investing in stocks or mutual funds involves the standard deviation. The standard deviation measures the volatility of the restaurant of the investments relative to an historical average. So if the return of an investment fluctuates from the historical average, then there'll be a higher standard deviation. And if an investment tool's value stays near the historical average, then you have a small standard deviation. So thus, a higher standard deviation can be one measure of the higher risk. Investors often wish to obtain the highest profit while minimizing risk, and this is often accomplished with what is sometimes termed a beta function. Now, in the standard deviation we talked about when we studied the statistics. But now what we're going to do is we're going to think about this in the context of a linear programming problem, this example 3, about investing. Mariana wants to invest up to $5,000 in stocks. The share price for CVS Health Corp is $81, and the share price for Target Corporation is 57. Based on the average of 10-year returns, CVS would produce a yearly profit of $11 per share, and Target would produce $4 per share. Mariana would like to obtain at least $520 in profit per year. A measure of risk for each of these stocks is the beta value. The lower the beta value, the less risk associated with that stock. So if the beta value for CVS is 0.62 and the beta value for Target is 0.24, how many shares of each stock should she purchase to minimize the risk as measured by this beta value? So let's set it up. First, we define our variables. Let X represent the number of shares of CVS stock to be purchased, and let Y be the number of shares of Target stock to be purchased. The information in the problem can be summarized in the following table, and the limits on the amount she has to invest and her desired profit. Let's talk about the constraints imposed by the cost of shares and the profits. So she is spending $81 for each $81 for each CVS share and $57 for each Target share. So the sum of these must be less than or equal to $5,000. Her profit, she wants to be bigger than or equal to $520, so this is 11x plus 4y is to be bigger than or equal to $520. Those are some constraints that we have. We also are going to have x being greater than or equal to 0 or y greater than or equal to 0, because she cannot invest negative in either one. And her composite beta value is 0.62 for every share of CVS stock and 0.24 for every share of Target stock. So to summarize the problem then, this is the linear programming problem to be solved. Minimize z equal 0.62x plus 24y, subject to 81x plus 57y is less than or equal to 5,000. 11x plus 4y is bigger than or equal to 520, and both of these have to be non-negative. So we graph the feasible region as shown here, and we find the corner points. And we plug the corner points in to the objective function. And we find out the minimum value of 29.326 occurs at 47.3 and 0. So she must buy a whole share of stock, so that would be 47 shares of the CVS stock. Now, in the VCM, and as homework, I'm going to ask you to do these problems, 13, 14, 15, and 18. So we will review this and we'll go through these. We'll do a setup and then we'll go through and try to have a solution to all of these. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. Now more than ever, take care of yourself and of each other. May God bless you all.